Now we are going to start with the second theory, that is VBT. What does it stands for? It is valence bond theory. So this theory was given by Pauling, L. Pauling, in 1930. Now let's see what does this theory says about the bonding in the coordination compounds. So this theory actually, like before I just read out the points given by it, I just want to tell you in a brief that what actually the Pauling want to say in this theory. He says that, see, whenever there is a metal ion, you know that there is a metal ion, right? So that metal ion has a vacant d orbitals. We all know that the metal ion is the transition and the inner transition metal, and that means it will obviously it is going to possess the vacant d orbitals. So because the necessary condition is that the metal should possess the vacant d orbital, right? And then we have the ligand approaching the metal ion. And like when the ligand approach, the metal ion, you can say that make available vacant d orbital to the ligands. Again, we have the metal ion with vacant d orbital, and whenever the ligand approach, it makes available those vacant d orbital to the ligands, right? And number of vacant orbital obviously indicates the coordination number. We have already done that. That number of vacant orbital is just indicated by the coordination number. So now we have the metal with the vacant d orbital, we have a ligand which is approaching, and now what is going to happen, these vacant empty d orbitals are going to hybridize. They are just going to hybridize, and as a result we will get a complex. So this is what the Pauling actually wants to tell you in this theory. Now what happens, like whenever the ligand approach, it has the vacant d orbital. Now the vacant d orbital are going to hybridize, and you know that on what factor the hybridization depends actually. It depends that what kind of orbitals the metal ion is just making available to the ligands. So it may happen that it make available its S, P and outer D d orbital, and it may happen that it makes available the penultimate, that is n-1 d and S and P. So according to that, the complex which is formed is classified into the inner orbital complex and the outer orbital complex. What is the difference? The difference is just that in inner orbital complex it is making the vacant orbital which it is making available to the ligand is the penultimate one, and the outer orbital it is making like the d orbital which is available to the ligand is the outer one. I will just tell you with an example, then we will just look for the points. See, if in case I tell you that this is my d orbital, right, 1, 2, 3, 4, 5, we know that in d subshell there are 5 orbitals. So I am just making 5. This is my S and this is my P. Right. So if in this case we observe that somehow if d orbital is completely filled, it is completely filled. So whenever the ligand will approach, so obviously it cannot make a vacant d orbital, the inner one. It cannot make available this inner d orbital available to the ligands. But here, like for example, I'll take this 3d, I'll take this 4s, I'll take this 4p, and I'll make one more orbital, that is 4d. Right. So if the 3d orbital is completely filled, so that is clear that it cannot make these orbitals available to the ligands. So in that case, which orbitals it will make available to the ligands? Obviously the outer one, that is this S, this P and this D. Right. So this is going to be the outer orbital complex. But if in case I say that there are vacant orbitals in the inner one also, so if the ligand will approach, obviously here it can make available these inner one also, this S also and this P also. So this is going to be inner orbital complex. So that means whenever the ligand approach, it just matters that what kind of orbital it is making available to the ligand, and according to that we can classify the complex as inner orbital or the outer orbital complex. So now it's time to look for the points. So just look at the board. So what does this valence bond theory states? As you already know, it states that bonding occur due to overlap of the orbitals. I told you that whenever the ligand is approaching, the central metal ion is making d orbitals available. So obviously why they are making orbitals available? Obviously they are going to show the overlapping. So bonding occurs due to overlap of the orbitals, and mainly what kind of orbitals? Obviously of ligand orbitals and vacant d orbitals of the metal atom. Now what happens if there is a rearrangement of electron required, then it is done. this point will be clear when I'll explain you with an example. So just keep this point aside for a moment. So next we know that there will be overlapping, followed by the hybridization, and as I told you that whenever the ligands approach, the hybridization can make use of inner D or can make use of outer D, just depending upon the condition of the metal atom. If the D is completely filled, so it obviously it is going to make use of the outer D orbital, and if this is the penultimate is not completely filled, then it can make use of the inner one also. And depending upon that, we have two kind of complexes, inner orbital complex and outer orbital complex, right. So that means our orbitals which can hybridize can be D in sequence of this n minus 1D, ns in np, or it can be ns, np and nd, right. So either of it we can use, and depending upon that our complex is going to be that, right. Now as far as the shapes is concerned, as we did in the Werner's theory also, that the secondary valency, that is the ligands actually decides the shape of the coordinate compound. So if there is a participation of 1s and 3p, then the shape is obviously going to be tetrahedral, and when it is going to be sp3, obviously when the coordination number is 4. And if it is making use of inner d orbital and coordination number is still 4, then the shape is going to be square planar. Likewise, if the coordination number is 5, that means 5 ligands are bound, and it is making use of outer d, the shape is going to be trigonal bipyramidal. And if coordination number is 6 and it is again making use of the outer d orbital, that is sp3d2, then the shape is going to be octahedral. And if it is making use of inner d orbital and coordination number still remains the same, that is the 6, that means d2 sp3, then again the shape is going to be octahedral. So this is how, by just looking at the hybridization, that whether it is making use of inner d or outer d, you need to just explain their shapes, that yes, this and this will be the shape of this compound. So just look at the example. Our first example is CONH3 whole 6 and 3 positive, right. So in this case, the oxidation state for the cobalt is 3 positive. Oxidation state for the cobalt is 3 positive. So let's write the electronic configuration from the central metal atom, that is for the cobalt. So when I write the configuration, obviously it is going to be argon 18, 3D first we fill 4s. So it will be 18, 19, 20 and 7 are left. So configuration is argon 18, 3d7, 4s2, right. So here I need to make 3 positive because its oxidation number is 3 positive. So that means I need to remove 3 electrons. So let us remove. So obviously I will be removing from this 4s and 1 from the 3d. So what I have left with? I have left with argon 18 and 3d6. So now let us make the orbitals for the better understanding. So I have this d orbital, this is my 3d, I have my 4s and then I followed by my 4p. Now how many electrons are present in 6, in d is 6. So let us fill it 1, 2, 3, 4, 5 and 6. As you must be familiar with the Hund's rule of maximum multiplicity, that the pairing won't take place until and unless each orbital is singly filled. So that rule of the atomic structure I have used here. So this is my configuration. So now I need to link 6 ligands. So that means I need to offer how many vacant orbitals? Obviously 6 orbitals we need to make available. So and now due to experimental studies, we have known that this compound is diamagnetic. Diamagnetic means there is no unpaired electrons. So that means here in this case I can see unpaired electrons. So that means in order to make it diamagnetic, I just have to pair them up. So let us pair them. So it is again d orbital. It's already paired. This I have paired, and after pairing I get this kind of thing. Right. Now I have to make available 6 vacant orbitals to the ligands. So let us count how many vacant orbitals are there which we can make available to the ligands. So it is 1, 2, 3, 4, 5 and 6. So what orbitals it is using actually? It is using D2, 1s and 3 for P. So obviously the hybridization is going to be D2sp3. So now here the ligands will just accommodate their lone pair and they will just get linked up, and this is my hybridization, that is D2sp3. So as you have seen here, what is the coordination number? You can easily count by just adding them. So it is 3, 4, 5, 6. Obviously the coordination number is 6, and as you can see there are 6 neutral ammonia molecules here. So this is being satisfied, that means our secondary valency is satisfied. Now as far as the shape is concerned, so we know that for D2sp3 we have shape octahedral. So obviously they will arrange in a octahedral manner. Now after doing that, it's time to just decide that whether it is an inner orbital complex or the outer orbital complex. So just look at the board, what kind of d orbital it has used actually. It has used the inner d orbital, that is the penultimate one, or the outer one. Obviously it has used the penultimate one. So that means it is going to be inner orbital complex, and they are actually low spin complex. As you can see that the spins, these electrons are actually paired up. So it is low spin complex, or you can say paired spin complex. And likewise, if we let us do a second example, it will be clear. So it is Cobalt F6. So now again, if we write for the configuration for the cobalt, obviously it is going to be the same, argon 18 3d7 4s2. Here the oxidation number is again plus 3. So what do I get? I get this thing, argon 18 3d6. So let's see for this what happens actually. So we have this configuration now. Now as far as its magnetic character is concerned, so by experimental studies we have known that it is actually paramagnetic. That means it possesses the unpaired electrons. So when you come to know that it is a paramagnetic, then just don't rearrange the electrons, don't pair them up, this thing, keep them as they are present. So it is this. Now we want to link 6 fluorine. We want to link 6 fluorine. So as you can see, we have not paired any electrons. So 3d orbital is it cannot make available this vacant d orbital. So what we are left with in that case? Obviously we are left with 4s, 4p and 4d. These are the orbitals which it has to you can say make available to the ligands. So let us count the 6 orbitals starting from the vacant one. It is 1, 2, 3, 4, 5 and 6. So these 6 will be accommodating the fluorine now in order to form a complex. And now like if we talk about hybridization, obviously it is going to be 1 for S, 3 for P and 2 for D. So it is going to be sp3 D2, and as far as the shape is concerned, we know that it is again octahedral because the coordination number is 6, and in this case if we talk about what kind of d orbital it has made available to the ligand, so we have seen that it has made available 4d, the outer one. So obviously it is going to be the outer complex, it is going to be the outer coordination complex, and it is also called as high spin complex because it has number of unpaired electrons in it. So this is how you are going to perform the questions depending upon the valence bond theory. So just keep in mind when you are doing it that it needs the overlapping of the ligand orbital and with the the metal atom orbital. And second is that do the rearrangement if required. If not required, do not disturb the electrons, let them present as they are. Third, you need to perform the hybridization, and hybridization can be depending upon what kind of orbitals you are using. It can be an inner orbital complex or it can be outer orbital complex, low spin or high spin. And moreover, one more thing, you need to focus on the magnetic character, because as you have seen in this example, when I took my whole question was just dependent upon this diamagnetic and the paramagnetic one, because if I I do not take this into consideration, then I won't pair them up, and in this case I just left them like this. So you need to be well versed that what kind of magnetic character it possesses actually, because after that only you are just going to perform the bonding in the coordination compound. So this is how the Pauling actually tried to explain the bonding in the coordination compound by giving the valence bond theory.